Hi, guys. I'd like to follow up with a new technique for visualizing data. This may be helpful to you as you create visualizations for your paper. Remember how we talked about how multiple regression creates predicted values? Technically, it's creating a fitted line, a best fit line through multiple dimensions of data, right? We can use that to our advantage to create plots where the y-axis is the predicted, say, voter turnout, or the predicted vote for Trump, and the x-axis is any particular predictor. On the one hand, we can always do this using a simple best fit line on a bivariate relationship. So, for example, if we were to use the election data set that you used in your group lab, we could always start off with a simple visualization. So, for instance, I am loading the tidyverse package and I just loaded in the elections data. We could always plot the relationship between, say, age and voting for Trump in 2016 like this. We could make X age median 2016. We can make the y-axis vote share Republican 2016. We could make a scatter plot, and we could use geom smooth method equals lm se equals false, and I got a, there we go. We can do that and see what that gives us. Okay, neat. That gives us a crazy mound of data. It sort of seems like a positive trend, but it's not really a very convincing visualization, right? And it shouldn't be, because we know that many things affect who you vote for, or how much a county votes for one candidate versus another. And so we would really want to control for some of these things, as you did in your lab. We would want to control for income, for age, for population, for gender, bunch of things, right? So what in the world would it look like? Would a good visualization look like after you'd controlled for all of these things? Well, the good news is we can use the model equation of an OLS regression line to figure that out. So for example, let's make a simple model. You could make a better one, I'm sure, but we'll just make a simple one right here, where we're predicting the percentage of the vote in a county that went to Republicans in 2016, i.e. who voted for Trump. And we're predicting it based on several explanatory variables: population, income inequality, I think this is like the Gini index, and the median age in years. So if we run that, we're going to get a model object called M, right? Here it is. And we can even just run that and see our model equation. Remember how I said that you can plug in any set of values for population, income inequality, age, median, and it's going to output a predicted value? This is really powerful. So here's what we can do. If we want to see how an outcome varies on the y-axis as one explanatory value varies on the x-axis, we could say, well, I'm going to feed this equation a bunch of values, and all of them are going to stay the same except for one variable, and that variable is going to be the x-axis. What does this mean? Well, if we scroll down here, we can create a fake data frame of data based on the original data, right? So we can say, hey, give me the mean income inequality score. Give me the mean population across these. We're going to keep all that. And now give me the median, make the median age equal to 0 up until 100. Let's see what this looks like. So we've made this new this data frame of fake data. And it's called new data. Huh. Okay, cool. So it looks like we have all values from 0 to 100 in terms of age, but we've held each row constant. So here's the really cool thing. We can use this function called predict to feed those into our model equation and output a predicted value for y, for this row, and for this row, and for the next row, and the next row, and the next row. So we can see as age changes while everything stays the same, how does voting for Trump change based on our data, based on our model. We can do this using this function. So let's talk through what this does. We use the predict function here. And in fact, I'm just going to use the predict function straight up. If we just say predict m, what happens? Predict m literally gives you the best fit line values. It gives you the same thing as fitted this. Okay. However, if we were to feed it new data, which we've called new data, you could call it whatever. So new data equals our new data frame. If we were to feed it some values, it would spit out predicted values for that. And we could even ask it. So let's add that in. New. I'm just writing this on top so you can kind of see what's going on. If we say SEFit, I'll explain this in a moment, it's going to output something that looks like this. Huh. Okay, the fitted values, something called SEFit, and a few other things that don't really matter. Great, so these are fitted values, and you'll notice we have perfectly 100 of them, I believe, because we go from 101, because we go from 0 to 100, right? In our age bracket up here. Cool, so we have generated predicted values. Now, these aren't really in a data frame format, right? So ggplot can't work with them. So we need to say, hey, please turn me into a data frame. That's called the asDataFrame function. It's new, but it's pretty easy to get a handle on. Great, so now it's in data frame format. That's much nicer. Okay, and we can actually use this thing called bind calls and say, hey, please remember to grab all the data that we inputted too. This is important because this is going to give us our x-axis. Right now we've got age median back in here, so we could easily plot the x-axis. Okay, so quick thing. se.fit. What is that? That's called the standard error. We have not talked about standard error in this class much. It's a little obtuse, but it's vitally important. Standard error is the standard deviation of estimates on a normal distribution. If your standard error is high, it is going to be, it means that your estimates might vary more, right? And if your standard error is high, it's going to be much harder to achieve statistical significance. That's because, remember how we made those permutation null distributions, those very nice normally distributed null distributions all that time? Well, we used permutations all those times to generate p-values. But there's also this special trick. The standard error is the standard deviation of them, right? And if you take the standard error and you multiply it by certain values, you hit on normal distribution the 95th percentile, or the 97.5th, or the 99th. It's this cool thing about normal distributions. So if we can generate the standard error, we can multiply it by a specific number, and it will tell us the 95% confidence interval. It will tell us the range in which we are confident that our prediction is true. Cool, right? I hope that makes sense. Feel free to follow up with questions, and I'm going to work with each group individually on what kinds of visualizations they want to make, so that you can produce something that's meaningful for you. This is just one route. Basically, you got your fitted value, which is the predicted vote share for Republicans in 2016. You've got your SE fit, which is how much it might vary. And we can multiply SE fit by a certain amount and use that to create our confidence interval. Okay, so let's run this and create a data frame called probs. That's just going to store our predicted values that we made up here. Guess we don't need that anymore. And then we can just plot them in ggplot. I'm going to plot it first so that you see what we're making, and then I'm going to explain what made each part. That wasn't supposed to happen. Gonna run it from the top. Goodness gracious. Okay, we'll work with this. What this did is it plotted the best fit line. That's pretty nice, right? This is the, it's not exactly the best fit line. It's the predicted voter turnout as these things varied. Now, it would be really nice if we could tell how that varied over time. So let's see what we've got here. So hypothetically, if we had our data set probs, we should be able to create an extra variable like, and I'm just going to select some of these. So fit, SE fit, and maybe age median. That way we can see them all. We should be able to create like an upper and lower bound for this line. What we are very confident, what we're 95% confident that the predicted value would be in. So the upper, this is a convenient shorthand. We can take the standard error, multiply it by 1.96, because, fun fact, on a normal distribution, the 97.5th and the 2.5th percentiles are 1.96 standard deviations from the mean. It's a dumb little fact, but it's really powerful. It means that we can use this to calculate a confidence interval. Okay, so if we do this, what do we get? Well, we get an estimate for the upper bound of our predicted probability, our predicted voter turnout. So at 0, it might be here, but we're 95% confident that's between here, here, and what we're going to make in a moment, which is the lower bound. So let's make that 2. That's going to be lower equals fit minus, not fiat, fit minus se dot fit times 1.96. Let's check this out. Great. So we can see that this is definitely lower than that one, right? So we're assuming that for if your age is 0, if your county's median age is 0, that's going to be within about this range, where this is the upper, and this is the lower, and this is the actual value. Okay, so let's try and figure out what is happening here. That is so curious. We could do it from scratch right above. So I'm going to use the ggplot function where I say we want the x-axis to be 2016 because we want to show like what happens as age increases. And we'd want y to be, oh, I think I figured it out. That's what it is. Okay. Well, I'm going to continue with the example while we're at it. Okay, we want y to be the predicted value for voter turnout. We're actually going to add something new here called y min and y max. Y min is the lower bound and y max is the upper bound. So we can literally say y min equals lower, y max equals upper. It's convenient. We could also, as we've done it here, I just actually wrote the original thing right here. So I just put that in instead. But I kind of like this way. And then we can use this new function called geom_ribbon. We can say, hey, make it blue. We can say, hey, make it transparent too. And we can say, please remember to plot a line along our y values. Let's see what happens. Ta-da! Pretty cool, right? So what happens before? Why wasn't it working? This was actually not intended, but I think it's kind of nifty. This function is pretty much the same as this one. It's virtually equivalent. So we could run this too, and it's going to work now. Great. Now it just has titles. Okay. Because we have this lapse function here. So what was different before? Well, before I had fit equals this times 100. And if we run this, we'll see that, oh, great. Well, our y-axis values have become more interpretable, but now we don't get our confidence interval. What the heck? Well, it turns out that we multiplied fit by 100, but we didn't multiply the upper and lower bounds by 100. So to really make it work, we would have to multiply. Actually, it's really just a pain. We would have to put this in parentheses, right? Like that. So really, everything did work. It's just that we can't see them because we're so zoomed out. So let's run this again, see what happens. Ta-da! We got it. Pretty cool, right? Okay. So these are two ways of generating predicted probabilities. The lower bound of your predicted value and the upper bound of your predicted value. And we use it, we calculate it using the standard error. The standard error is the standard deviation of our estimates. And it's from a hypothetical null distribution. Neat. We can do it by mutating before we plot it, or we can do it by building it right in the ymin, ymax function. these create really nice plots. Sometimes I like to say, hey, here's the effect of age, and here's the effect of something else going at the same time. It's a lot of options. If you're interested in learning more, try it out. You can shoot me an email if you have questions, if you have code you want my thoughts on, and I'm excited to see what you cook up. Thanks for your time.